In this problem, we'll be finding the electric field due to a continuous charge distribution. This problem can be fairly lengthy and at times will involve pretty technical integrals, but it will set the stage for Gauss's law. And Gauss's law will allow us a method in which we can exploit symmetries to bypass performing these integrals as we're doing today. Let's take a look at the problem statement. Now in this problem, we're asked to find the electric field at the center of a semicircle which has a continuous charge distribution. The approach here will be to find out the electric field from a particular part of this charge distribution, and then once we have an expression for that, integrate that over the entire region. Before we do that, let me just get an intuition about which direction the field will point, and we'll check that our answer is indeed correct with our intuition. So breaking this up into two parts, we have a positively charged quarter circle up here, and if I just consider that part by itself, which direction will the field point based on that? Well, I can first take a look at the symmetry. The symmetry, it's symmetric about this particular line. In other words, if I flip it on either side, it's symmetric there. So we know we can't have a field pointing in this direction or that direction. The field can only point down and to the right or up and to the left. And also, because we know it's positively charged, the field will generally point away from the positive charge. So right here, it's going to point down and to the right, away from this positively charged region. So the field due to that first section points kind of down and to the right. Similarly, if we do the same thing down here with this is negatively charged, symmetric about this line, so it can only point up and to the right or down and to the left. It's negatively charged, so the field at this point will point towards the charge, so it's going to point down and to the left. The magnitudes are the same because we have basically the same geometry here, and the magnitudes of the charges are the same. They're just different signs. So these are the two fields. If I add them up using superposition, I can find the net field. The net field is the sum of these two vectors, which points straight down. What we expect, therefore, is that the net field due to this entire charge distribution should point only in the negative y direction. And we'll verify that with the mathematics. So let's go ahead and do the math. What I'll do first is try to find the electric field from the top quarter circle, and then we'll do the bottom quarter circle in a similar manner. So the top quarter circle, I'm just going to redraw it up here. I'm going to kind of draw a dotted line. So what I'm going to do, like I noted earlier, is that you're only going to consider a single part of this continuous charge distribution. And I'll just say, let's consider this little part right here. And you don't want to choose it at the end. It's better to choose it somewhere in the middle of the charge distribution. I'm going to say that guy has a charge of dq. All right? And dq just means that it's a small amount of charge compared to the whole thing. And it has a little bit of length, which we call ds because it's an arc length. S is typically always used for arc lengths, so it has a small arc length, ds. It subtends a small angle of d theta. And then it has a radius, it's at a radius of r, everywhere is r. And what we're going to do is determine what is the field due to only that one particular section of charge. So that one guy is going to create a field that points, well, the charge is right here, it's going to point down and to the right, basically just in the radial direction away from that. And we call that dE. Again, we're calling it D because that's not the field due to the entire charge distribution. It's only the field due to that single portion. So I just use D to indicate that it's a small field part. Now what we're going to do is find an expression for dE for the magnitude of it first, and then we'll break it up into components and integrate over those components. So first, let's just find the magnitude of the dE, which is by Coulomb's law. The magnitude of an electric field due to a single point of charge is the Coulomb constant times the amount of charge divided by the distance between where the charge exists and where you're measuring the field squared. All right. So now we have this in terms of dq. We want to get this in terms of a variable which we can integrate over, which is some sort of length or area. So I want to get this in terms of a length. And the way to do that is to rewrite dq in terms of, this is kind of a general trick. You're always going to write this in terms of, this is a charge. Write it in terms of charge per length, or in some cases charge per area if you're doing 2 dimensions, times the length. This is the same thing, obviously. Now the charge per length is, well, we always call that lambda, just by convention. And then the length of this is however long this section is, which is ds. So this thing has an arc length of ds. Now lambda is a charge per length, so we're not given that explicitly, but we do know how long the section is because we have the radius. And we also know the total charge on it. So the charge per length we can easily find by dividing these guys. So the charge is q. And then the length is however long this quarter circle is, which is pi over 2 times r. Remember, the arc length of any part of a circle is always going to be the angle it subtends times the radius. The angle this guy subtends is 90 degrees, and the radius is r. So that's your lambda. And then ds, we also want to write that in terms of an angle we can integrate over, which is going to be d theta. That'll be easy to integrate over. So ds, again, this is an arc length, and its length is going to be d theta times however long the radius is, so r d theta. All right, so this is an expression for dq, and we have it as we wanted it in terms of a bunch of constants. R is constant, q is constant, all that stuff is constant. But d theta is a variable which we can easily integrate over. So now let me rewrite dE in terms of this guy. So the magnitude of the field due to that single point of charge is the Coulomb constant times this expression all divided by r squared. All right, so that's the magnitude due to this point of charge. What we need to do now is break it up into components. And we're going to break it up into the x component and the y component. And there's two ways to do this. When you do this, you can either think of the angle this makes with some arbitrarily chosen direction, and then put in the signs by hand, whether it's positive or negative. Or you can always just treat the angle from the positive x-axis. And if you do that, the x's are always cosine theta, and the y's are always sine theta. And the sine takes care of itself. So I'm going to do that method. And so what that means is that the x component is the magnitude times cosine theta. And if I want to find the field due to this entire quarter circle, I have to integrate this over the entire quarter circle. So the field due to the positive charge, say positive q, is the integral of this guy. Let me say x too, because it's in the x direction. Integrated over all of d theta. But what I need to find out here is I need to find out the limits of integration. So the limits of integration here, that's the one you have to kind of think about it visually. So what you always want to do for this is always integrate in the counterclockwise direction. And so if I do that, I'm going to start by integrating this part of charge and then integrating all these charges all the way down. Now, if I look at that part of the charge, which direction does the field that it creates point? It points downward. Okay, and so this field points in the negative, or in the 3 pi over 2 direction. Right? So it points in the, this is 3 pi over 2, 270 degrees direction. So I'm starting at 270 degrees, or 3 pi over 2 radians. And then as I go around, the field moves like this. And then this part of the charge creates a field that points in the 2 pi direction. You don't want to use 0 because you want to increase the angle. So you go from 3 pi over 2 to 2 pi. Those are the limits of integration. Now what you have is an expression only in terms of theta and a bunch of constants, which you can integrate. So go ahead and integrate this expression, try to get a value for that, and we'll come back and do the y component. So when you carry out the integration here, you're basically going to have a bunch of constants times the integral of cosine theta d theta, which will give you sine theta. And then when you plug in the limits of integration, you end up with the following. You get ke times the total charge divided by this value, r squared, and you end up getting a positive value. So this makes sense. As we indicated earlier, we expect that the electric field of the positive q, the x component, should point in the positive x direction. Now let's carry out the same thing for the y direction. So we have the field due to the positive charge in the y direction is going to be given by the integral of dE. dEy is just going to be dE times sine theta. So it's going to be dE times sine theta d theta. And then the same limits of integration. And so go ahead and do that on your own, find a value for that, and just make sure that the sign makes sense with our intuition. Go ahead and take a minute to do that now, and we'll come back and take a look. So now carrying out the integration, we have the integral of sine theta d theta will give us minus cosine theta. And then if you evaluate that from the limits of integration, you'll get the same thing as the x component, except that it's negative. And this does seem right based on our earlier intuition, because we saw that the electric field due to this positively charged quarter circle will give us a field that points down and to the right, which is a positive x component and a negative y component. So the science kind of makes sense. The magnitudes seem about right because they're both the exact same magnitude, and we expected something going down at a 45-degree angle. Now what we're going to do is we're going to find out the electric field due to the bottom quarter circle. You could probably use intuition really quick and just figure out what those are, because we know they're going to have similar magnitudes. We just might flip the signs. But I want to have you guys practice a little bit determining what the limits of integration are, because that's the tricky part. So set up an integral for the x and y components similarly to as we did here, and then determine the limits of integration, carry it out, and make sure that your signs are correct. Go ahead and try that now, and we'll come back and take a look. Now for the bottom quarter circle, I've done the exact same picture here. We have a little bit of charge notated here, and what we're going to do is find the field due to that negative charge. Because it's negatively charged, the field, of course, is going to point towards it. And so for that particular portion, the field will point kind of down and to the left. And it's going to have the same magnitude because all the constants are the same as in the top quarter circle. In particular, the charge density is the same, and the length is the same and everything. So the magnitude will be exactly as before, which, if we recall, that was Ke, and then the charge density was Q over pi over 2r. And then this is the ds, is r d theta. And then finally, you can divide by the radial distance squared. All right, just to be clear about this, even though the charge here is minus q, you're not going to plug in a minus q for that value because the magnitude itself has to be positive. So you're going to use the absolute value of the charge, which is q. So this is going to be a positive number. When you do the angles and the components, the signs will take care of themselves, whether it's plus or minus. So this has to be positive, though. Now, finally, we're going to find the components. So if I'm looking for the component in the x direction, it's going to be the integral of the magnitude times cosine theta. And then we have to find the limits of integration. So we're going to do the same thing as before, always integrate in the counterclockwise direction. We're going to start right there. So right there, which direction does the field point due to the charge right there? And that's going to point directly at it because it's negatively charged. What direction is that? It's the pi direction. And then finally, just moving that all the way around, it's going to eventually end up at the 3 pi over 2 direction. Okay, so there's your integral. You can plug this in. You have everything in terms of a single variable. And when you carry that out, you'll find that the x component for the bottom quarter circle is equal to minus KEQ divided by this guy. Right? So it's the same magnitude as this x component, but it's negative. And then if you do the same thing for the y, but using sine theta, same limits of integration, you'll find out that it equals the exact same thing as that. So ultimately, what we get for the field on the negative q portion is minus KEQ pi over 2 r squared. And the same thing for the y component. And then so what we see is, as we expect, the x components cancel. In other words, if you add up this x component and that guy, they cancel to 0. These guys double. So as we had first looked at our intuition, we have that the x component does cancel and the y component is all that matters. When you add those up, the net field, due to the entire continuous charge distribution, is 0 for the x component, and then minus 20.62 newtons per coulomb for the y direction, which, written in unit vector notation, is minus 20.62 J newtons per coulomb. Okay, so there we have it. The answer we got ultimately did kind of align with our intuition. So it's always good to start out the picture, get an intuition for which direction it'll point, and then if you can determine that some of the components will cancel, don't waste your time finding them like we did here. Let's go ahead and summarize. In this problem, we were asked to find the electric field due to a continuous charge distribution. First, we found an expression for the magnitude of the electric field from a small differential section of this distribution. Then we decomposed this magnitude into components and integrated those components along the charge distribution. Finally, we added all vector contributions to find the net electric field. I hope this problem was a useful introduction into solving electric fields for continuous charge distributions. If you have any comments or questions for this video, please leave them on the link attached to the video, and we'll see you next time.